Modeling curves using logarithms. Now we come to the point of this tutorial and preceding lessons, which you should read first if you are not familiar with all concepts, that is to explain how to model curves using logarithms. First, we will explain what modeling curves means. Modeling curves is a widespread method used in experiments when a collection of data is available. Thus, modeling curves using logs means to transform curves into straight lines, which not only helps find new values besides those collected by the experiment but also to find the curve's equation, if it is missing. There are two types of functions that require curves modeling using logarithms. 1. Functions of the form y equals kx to the power of n. The process of modeling curves expression by the equation above requires the original function to be written in logarithmic form. This means that if we have the original function in the form, we have the following shown on screen. Where k and n are coefficients, numbers, and x is the independent variable, we must take the logarithm of both sides to obtain, we have the following shown on screen. Or we have the following shown on screen. Given that k is a constant, so will log k be as well. Therefore, we obtain a form of this function that is very similar to the formula of a linear equation, linear function. Recall the simplified form of a linear equation explained in tutorial 9.1, we have the following shown on screen. Where the coefficient m represents the gradient of the line and n is the constant of the equation, here, of the linear function. If we plot the values of the logarithmic function on the graph, we will obtain a curve like those discussed earlier. This is not very helpful in filling a data table with other values, as this would require calculating the y value manually for every x value considered. Therefore, we model the curve by expressing on the horizontal axis not the x values but the log x ones instead. Likewise, on the y-axis, we now show the log y values instead of the y ones. In our case, the coefficient n of the logarithmic function acts as a gradient for the straight line after modeling the curve. Modeling the curve is very important for another reason as well. It helps us understand whether two quantities are in an exponential relationship or not. Thus, if the values collected produce a straight line after modeling the curve, then the original curve shows another function that involves some exponentials, but it is not a pure exponential function as the variable is not in the exponent. For example, let's consider a set of data where the number of rare minerals found as a function of the number of detectors used is shown in the table. We have the following shown on screen. Let's try to identify any relationship of the form y, x, equals kx to the power of n. If it exists, the table must transform in such a way that the first row must contain the log x values and the second row the corresponding log y values. We have the following shown on screen. When these points are plotted on a log y vs log x graph yields, we have the following shown on screen. The dashed line shows the trend line, sometimes called the best fit line, which is straight. This means the original relationship between x and y is of the form, we have the following shown on screen. Model to the above graph through the logarithmic relationship, we have the following shown on screen. Now let's calculate the gradient n of the line, which corresponds to the exponent of the original function. We have the following shown on screen. Since all measurements contain their margin of error, we take the rounded value n equals 1.6 as the exponent of the original function. Now, we have to calculate the coefficient k, which in the corresponding logarithmic function is given by log k. It represents the intercept of the line with the log y, vertical, axis on the linear graph shown above. In other words, it shows the initial vertical coordinate when the horizontal coordinate is 0. Given that we have log k equals 1.079, which corresponds to the original value of 12 rare minerals when a single detector is used, then K equals 12. Hence, the original function that shows the relationship between the number of detectors used and the number of minerals found has the form. We have the following shown on screen. As mentioned earlier, knowing the general formula of such a function allows us to make predictions on situations where more elements, here detectors, are involved. In other words, we can make a prediction on how many rare minerals we can find by using more than 5 detectors. Example 1. A. Check for any relationship of the form y, x, equals k, x to the power of n between the quantities involved in the data set collected during an experiment shown in the table shown in the following on screen. B. If such a relationship exists, find the approximate y value for x equals 20. Solution 1. A. Let's create a new table where the values of log x and log y are placed instead of the original x and y values. We have the following shown on screen. We take log 0 equals minus infinity because 10 minus infinity, sup, equals 0. Indeed, the graph of a logarithmic function y equals log x never touches the y-axis, as the independent variable can only approach 0 but never be 0. The more the x value points towards 0, the more the corresponding y value points towards minus infinity. Now, let's plot the log y versus log x graph for this data set. We can skip the first column, as both values are minus infinity and are not shown in the graph. Thus, we have the following shown on screen. The dashed line shows the trend line, the best fit line, which is straight. This means the original relationship between x and y is of the form, we have the following shown on screen. Model to the graph through the logarithmic relationship, we have the following shown on screen. Now let's calculate the gradient n of the line, which corresponds to the exponent of the original function. Again, let's skip the minus infinity values. We have the following shown on screen. Since all measurements contain their margin of error, we take the rounded value n equals 2.5 as the exponent of the original function. Now, we have to calculate the value of the coefficient k, as it is not actually shown by the graph. Since the function has the form, we have the following shown on screen. We can substitute in it a pair of coordinates from any point shown by the original table, for example, x equals 4 and y equals 8. In this way, we have the following shown on screen. Therefore, the original function indicated by the first table, and also from the second table and the graph, we have the following shown on screen. B. Following this trend, for x equals 20 we have the following shown on screen. Two functions of the form y, x, equals a b to the power of x. These functions are considered as pure exponential functions as the independent variable is in the exponent. The transformation made in such functions for modeling them, we have the following shown on screen. This form is similar to that of a linear function where log b is the gradient and log are the constant of the line. Therefore, this time we have to plot the log y versus x graph instead of log y vs log x1. This means that only the vertical axis needs to be transformed. For example, if we have the set of the following data that shows the presence of bacteria in a food sample left outside the refrigerator, we have the following shown on screen. And we want to investigate any exponential relationship in order to find whether they are resistant to environmental conditions. If there is any sustainable exponential relationship, this means the bacteria are resistant and keep growing in number according to a certain proliferation rate. Then we follow the procedure described earlier in theory. Thus, it is obvious that if there is a relationship between the variables similar to those explained earlier, then the value of the coefficient b of this function is 37, as this is the original number of bacteria in the sample. This is because a to the power of 0 is equal to 1. Hence, the possible function has the general form. We have the following shown on screen. Now, let's try to confirm this possible exponential relationship by modeling the curve by using logarithms. This means we have to consider log y instead of y in the above table. In this way, we have the following shown on screen. When plotting these values on a log y versus x graph yields, we have the following shown on screen. The trend line indicates a linear relationship. Therefore, we have a function of the form. We have the following shown on screen. The procedure used to find the missing coefficients is as follows. Step 1. First, we determine the constant log a. This represents the value of log y for x equals 0. In other words, it represents the initial vertical coordinate of the line, i.e. log a equals log 0. From the second table, we know that for x equals 0, log y equals 1.568. Therefore log a equals 1.568. Hence, we have the following shown on screen. Step 2, then, we calculate the gradient log b of the line using the relation. We have the following shown on screen. Taking the initial and the first coordinates yields, we have the following shown on screen. Step 3, then, we calculate the value of b through the relation. We have the following shown on screen. In this way, we obtain the value of b in the original function. We have the following shown on screen. Hence, for the original relationship between the number of days elapsed and the number of bacteria in the sample, we have the following shown on screen. Example 2. The mass of an avalanche in kilograms as a function of the sliding distance from the top of a mountain expressed in decameters, dam, where 1 dam equals 10 meters, is shown in the table shown in the following on screen. Find a. the mass of avalanche v's sliding distance function determined with the data. b. the mass of the avalanche when the slope slides down the mountain to 200 m below the original position. Solution 2. A. the mass of the avalanche increases more than twice for each decameter when falling down the top of the mountain. Therefore, there must be some sort of exponential function involved. However, to be confident of this hypothesis, we find the logarithms of all y values representing the mass, and see whether there is any linear relationship between the new values obtained and those of the distance. In this way, we obtain the following table shown on screen. When plotting the data in the log y v's x graph yields, we obtain the following table shown on screen. Therefore, it is already certain that the original function has the form. We have the following shown on screen. Now, let's find the coefficient a. From the original table you can see that for x equals 0, y equals 0.320. Since b to the power of x equals b to the power of 0 is equal to 1, then a equals y 0 equals 0.320. As for the base b, we can substitute the coordinates of any point in the original graph. For example, for x equals 1 and y equals 0.740, we have the following shown on screen. Hence, the snow mass of the avalanche increases for every falling decameter according to the exponential function. We have the following shown on screen. b. If the avalanche slides down for 200 meters or 20 dam, x equals 20, its mass becomes the following shown on screen. This is a very large amount of snow, although in reality a part of the snow collected in the avalanche detaches from it on the way. More importantly, the remaining part is large enough to cause harm to property and people. How to understand a priori whether a function is of the form y, x equals k x to the power of n or y, x equals b a to the power of x. This is not merely a question of experience, although experience plays an important role in guiding your intuition towards the right path, but of the reasoning as well. You must take a look at the first 2 or 3 columns of the table and see whether there is any kind of geometric progression in the values. In this case, the function most probably has the form y, x equals b a to the power of x. If you are not able to identify such a relationship that resembles a geometric sequence, but the values look more like forming an arithmetic one, albeit not exactly, then try the first option, i.e. y, x equals k x to the power of n. That is all for lesson 13.3.5 and the end of tutorial 13.3. To continue this chapter, please watch 13.4, Introduction to Natural Logarithm Function and its Graph. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.com.